Hello everyone, welcome back to the channel. This is another video on DC machines. In previous video, I had explained the construction as well as the working principle of both DC motor and generator. From the construction, it's evident that the same machine can work as generator as well as motor. If you haven't checked that video, you can check from the link which is available in the description box of this video. For generator, we need magnetic field, conductor, and one of them should be stationary and other should be rotating so that there is flux cut by the conductors. And when there is flux cut by the conductor, so there is an induced EMF in the that conductor. That induced EMF can be collected from the armature winding through the commutator and brush assembly. So what's the value of that induced EMF? That we need to find, and for that in this video I'm going to derive the EMF equation of the DC machine. It had also been explained that this generating action takes place in the motor as well once the motor starts rotating, since and at that time the rotating conductors are placed in the stationary magnetic field and there is flux by the cut by that conductors, and when there is flux cut by conductors, so there is an induced EMF in the that conductor, and that EMF is known as back EMF. What's the value of that EMF? The expression will be same for both motor and generator. After driving the EMF equation, I will explain different types of DC machines and their electrical equivalents. So let's start with the EMF equation. For EMF equation, let's say phi is the useful flux per pole in Weber. P is number of poles. So number of poles are always in even numbers. Z is total number of conductors. N is speed of armature rotation in RPM, that is revolutions per minute. A is number of parallel paths. Now, what's the meaning of number of parallel paths? If you remember in the previous video, I had explained that in order to increase the current carrying capacity, the conductors are connected in parallel. So, when conductors are connected in parallel, so obviously there is current division. So, how many number of parallel paths are available in the machine for the flow of current? That is the number of parallel paths. So that is given by A. Now what's the value of A? That I will also explain once we are done with the EMF equation. So effective number of conductors in each parallel path will be Z by A. Since total number of conductors are Z, so Z by A is the number of conductors in one parallel path. Now we need to find out the EMF. Let's say E average is induced EMF in one conductor, and Eg is generated EMF. Since in parallel the induced EMF or the voltage that remains same, so EG will be equal to average induced EMF in one conductor into number of conductors in one parallel path. It doesn't matter that how many number of parallel paths are there in the machine, the voltage across them will remain same, current will be different. So total induced EMF in the machine will be equal to average induced EMF in one conductor into effective number of conductors in one parallel path. Now we need to find out that what's the value of this E average. This E average will be equal to flux cut per revolution upon time taken for one revolution in seconds. So flux cut per revolution will be calculated from flux and number of poles. Phi is the useful flux per pole, P is the number of poles. So in one revolution, the total flux will be P into phi. Since this flux will be associated with all the number of poles, so it's P into phi. And how much time is there, that we can calculate from the speed. Now the speed n is in revolutions per minute, so we have to calculate it in per second. So in per second it will be n by 60. Time taken for one revolution will be 1 upon n by 60. So which gives us the value of E average as P phi n by 60. Once we use the value of E average in generated EMF equation, then EG will become P phi n z by 60A. So this is the EMF equation of the DC machine. For motor, we write this as EB is equals to P phi n z by 60A. Just to denote that this is the back EMF which actually opposes the applied voltage. So that's why it's written as EB instead of EG, while EG is the notation commonly used for the generator, that is for induced EMF in the generator. Now this equation can be expressed in terms of angular speed as well. So E can be written as P phi z upon A to n by 60. N by 60 is speed in revolutions per second. So if we multiply this equation by 2 pi as well as divide, so this equation can be written like this. So P phi z upon 2 pi A, 2 pi n by 60, so it becomes 2 pi n. So this 2 pi n is the angular speed. 2 pi n is angular speed, which is written as omega m. In this equation, P, Z, 2 pi and A, they will remain constant. Since once a machine is designed, the number of poles will remain same, number of parallel paths will remain same, number of conductors that will remain same, and 2 pi is constant. So they are denoted by Ka phi omega m, where Ka is constant, which is equal to Pz upon 2 pi A. So this is another way to write the EMF equation, which can be written for both motor as well as generator. Now, depending upon which equation we are interested to use, we can use the equation either in this form or in this form. Now, coming to that, what is the number of parallel paths? Now, number of parallel paths are dependent upon that which type of winding we are using in the armature. So, there are two types of winding in armature. One is lap winding, second one is wave winding. In lap winding, the ends of each armature coil are connected to adjacent segments on the commutator so that the total number of parallel paths are equal to total number of poles. So A is equal to P, while in case of wave winding, the ends of each armature coils are connected to the commutator segments some distance apart so that there are only two parallel paths. So A is equal to 2 in case of wave winding. Since number of parallel paths are more in case of lap winding, so they are used for high current DC machines while the wave winding is used for lower current DC machines. So this lap winding and wave winding, these are according to the construction, and once designed they will remain same. We can't change them. So it will always be given in the problem whether the machine is lap wound or it's wave wound. Accordingly, you have to choose the number of parallel paths. Now, once we have the EMF equation, we can draw the equivalent of DC machines. Whether it's motor or generator, we can draw their equivalents. So what we have in the DC machine, we have a armature winding and a field winding. So field winding is always supplied from the DC source, while armature, depending upon whether it's motor or generator, may be supplied or maybe we collect the output from that. The field winding is placed next to the armature, where armature is represented by a circle showing the generator or motor that they are rotors as are in the form of cylinder or circle surrounded by two brushes. These are representing the brushes, and here we have the voltage, and field winding is placed like this. So this one is the representation of field winding. Field winding will have resistance RF, since it's not possible to have a winding without the resistance. Similarly, the armature winding will have the resistance RA. Across these terminals, the voltage is VT. Here the voltage is VF. Current is always flowing in the field winding, whether it's motor or generator. In this we have induced EMF. Now this is the equivalent which we can say of motor and generator if we know that what's our direction of current in the armature. So now we can say this one is for motor and this one is for generator. In generator, current is flowing away from the armature, which is known as IA, and the induced EMF over here is denoted by EG, while in case of motor, the induced EMF is denoted by EB. The current is flowing from the supply side towards the armature since we give the electrical energy as input to the DC motor. Field current is remaining same. So this is how the electrical equivalent looks like. Now what we see in case of generator over here, the terminal voltage and this generated EMF, they will be related since generated EMF is over here. If we have to apply KVL, then the equation will be minus EG. We haven't shown any resistance over here by the resistance symbol, but the armature winding will have resistance. There will be drop across that. That will be IARA plus VT will be equal to 0, or EG is equals to VT plus IARA in case of generator. This is known as voltage balance equation. Similarly, we can write the voltage balance equation in case of motor. Now in motor, we have minus EB. Then since the current is flowing in opposite direction, so minus IA RA plus VT equal to 0, or EB is equals to VT minus IARA. So the difference is whether this armature drop is added to the terminal voltage or subtracted from the terminal voltage. So what we see over here, that this back EMF is opposite to the terminal voltage. That's why the name given is back EMF, that it tries to oppose its cause, and cause is that we have applied the voltage, and because of that conductors are now became current carrying conductors, and it is trying to oppose that voltage only. Now in this representation of generator and motor, what we see that there is no connection between the field winding and armature winding, but there is possibility that armature winding and the field winding, they have the connection. So based on that, we have different types of DC machines. Now types of DC machines are actually based on that how we are giving the supply to the field winding. So the production of magnetic flux in the machine by circulating the current through the field winding is known as excitation. So the types are given like separately excited and self-excited. Separately excited means there is no connection between field winding and armature winding, means this is actually representation of separately excited machine. So if machine is working as motor, then we need a different DC source for the field winding and different DC source for the armature winding. And if it is working as motor, we need to give the supply from the DC source which has no connection with the output from the armature of this DC generator. While in case of self-excited, the armature and field have the connection. So how they are connected? Based on that, we have three different types of self-excited machines. Shunt excited, it means the field winding is connected in shunt with the armature or in parallel with the armature. Series excited machine, where field and armature are connected in series, and if both series and shunt are combined together, then we have third type of machine which is known as compound excited. The compound excitation is further of four different types. So I will consider this compound excitation later on in a separate video. And in this video, I will consider only shunt excited and series excited machine. So starting with the shunt excitation or shunt excited machine, I will draw the equivalents for both motor and generator. The armature winding, field winding is connected in parallel to this, and here we have the terminals. The equivalent is same for the motor as well. The difference lies in the flow of current. So this one I am going to use for generator. So in generator we have induced EMF EG. The resistance of this armature is RA. The field winding which is connected in parallel, it is having resistance RSH, or you can write it as RF as well. RSH is just to show that this field winding is connected in shunt with the armature. Terminals where the terminal voltage is VT. Now this armature is supplying current IA to the machine, which will get divided into two parts. One is the field current which will flow through the field winding, and second one is current IL, known as load current or line current. This current will flow when we connect any load between these two terminals. So it's known as load current or line current. So here we can apply KCL to write the relationship between these three currents, that IA is equal to IF plus IL. The voltage balance equation that remains same, that EG is equals to VT plus IARA. At the same time, what we see that the voltage across this field winding, that is VT. So IF can be calculated from VT and shunt resistance. So these are the relationship which we need to use in case of solving the problems related to the DC shunt machine. And the power output of this generator, that will be equal to output voltage into output current. So that is VT into IL, since VT is the terminal voltage and IL is the load current. Now moving on to motor. In motor we have back EMF induced. Shunt field winding has resistance RH, RSH, armature winding resistance RA. VT is applied terminal voltage. Since electrical energy is the input to the DC motor, So current IL will start flowing from the supply side towards the motor. It will get divided into two parts. One is as field and second one is the current in the armature. So this is the representation of motor. Now if we apply KCL over here, then IL is equals to IF plus IA. So this difference must be understood, that what is the difference? The direction of line current and armature current, they are opposite in case of motor and generator. Since generator supplies the current from armature towards the load and motor withdraws a current from the supply side, and that current is divided among the armature and field winding. And the direction of field current will remain same in both the motor and generator, since we always need to give the supply to the field winding. Now the question comes to us that how the initially induced EMF is there, since we need to give the supply to the field winding from this armature only. So for the shunt excited generator or series excited generator, we have to design them so that they have residual magnetism. There is a small flux and that flux is cut by the conductors present in the armature, and once there is flux cut, so there is an induced EMF and that voltage starts building up. So there is voltage build up procedure that I will also explain later on in a separate video. Once that starts increasing, then this field current starts increasing and it goes on. So in case of motor, the voltage balance equation is EB is equals to VT minus IARA. IF is same as what we had in case of generator, since IF is equal to voltage across this field winding upon resistance of the field winding. In this case, we have power input, which is equal to input voltage VT and input current IL. So usually in the rating of DC machines, the line current and power input is given in case of motor, and in case of generator the power output and the current as output to the load that are given. Now moving on to the next machine, that is series excited DC machine. Now from the name it's clear that armature and field winding, they are connected in series. So armature winding and field winding, they are connected in series. Here we have terminal voltage. Now what we see over here, since they are connected in series, now the current, different currents, they will have same value. If this one is for generator and this one is for motor, in generator we have induced EMF EG, current IA, through field winding IF, and through load we have line current IL. So IA, IF and IL, they are same, and in case of motor EB, it will withdraw current from the supply IF and IA. This IA, IF and IL, they will have same value. The voltage balance equation is now changed with a little bit modification, that VT will be equal to EG minus IA RA plus RSC, where RSC is the series field winding resistance and RA is the armature resistance. RA and RSC. While in case of motor, VT is equals to EB plus IA into RA plus RSC. This is due to the fact that the direction of current is now reversed. RA and plus RSC, because two resistances are now connected in series. Again, the power output in case of generator is Vt into IL, while in case of motor we have power input which is equal to Vt into IL. Now, based on the relationships which we have derived for the shunt excited machine or for the series excited machines, I will solve different numerical problems in the next video. If you felt that this content is helpful for you, please consider sharing it with others and do consider subscribing the channel. Thanks for watching the video.